Hello, this is Lab 6. The main two topics of Lab 6 are power series and parametric functions. For SymPy, I will use two variables. I will use x as our usual variable, and I will use t for parametric functions. So first we will start with power series. To create a power series for a function, we can use series command from SymPy. It will have four inputs, f as a SymPy function, x is the variable, a is the number around which we're creating the series, and n is the degree. More specifically, if I want to have a power series of degree 5, n should be 6, so the series is up to that point. Also, if a is omitted, then by default it will be 0, so you will get Maclaurin series. So here's an example. Let's say we'll have exponential function. So we will create series of the exponential function around 0, since I'm omitting a, and n will be 6. So that means the series will be up to degree 6, so it will have degree 5. This is what it will look like. Notice that I will have this term here, besides my usual terms of series. This is the big O notation. In essence, it's just the degree of the next term. So the next term would have degree 6. Let's do another example. Let's say now I'll have a series of the same exponential function, but now it's going to be around 1. And so here it is. Now normally we're going to treat this partial power series as the function, as a polynomial, and therefore we don't want this big O notation at the end. So for the most part we will have to remove it, and it's quite easy to do. We can use .removeO method. So for example, if I want to have this series of degree 5, but without big O, I will have sp.series f(x) n equals 6, and then I will say .remove O with parentheses. And now as you can see, it's just a normal polynomial. Now that it's normal polynomial, we can do many other things. For example, we can plot it, we can find derivative, we can find integral, and whatever you need to do. So for example, let's plot it in this case. So I will lambdify my polynomial. I will also lambdify my actual function, so I'll plot both of them. I will plot function in red and my approximation in blue. I'll plot my axes, and I will do a legend since I labeled everything. So let's see what it looks like. So as you can see, in red I have my function, and in blue this is the Taylor polynomial. Next part is about parametric functions. Now dealing with parametric function is quite simple in Jupyter. So in this case we will try to plot it, and we'll try to find one integral related to parametric functions. So let's say I am given the following function: x of t equals to this expression, y of t equals to this expression. In this case, t is the parameter. So I want to plot it. So we will define both x and y of t in SymPy, and then we will lambdify them. I will use here xt, yt, so that I don't have to use x and y, because I already defined x as the variable for SymPy before, so I don't want to reuse it. Let's run it, and now we will plot it. So the main part is here. X of t and y of t are x and y coordinates, and so this is exactly what I will write here. The x coordinate will be x of t, and the y coordinate will be y of t. Now t values will go between 0 and 6 pi. I have chosen here 6 pi because this is actually a periodic function, and its period is exactly 6 pi. So try to figure out why it's exactly 6 pi, because you will have a very similar problem on this problem set. So now let's run this command, and here's our curve. As you can see, it just loops around many times. So next, let's try to find the length of this curve. We know this is a periodic curve, and in fact we know the period is 6 pi. It's given to us already. So we will use the following integral to calculate the arc length. So here, this is the integral from a to b, where a and b is the range for t, of square root of derivative of x with respect to t squared plus derivative of y with respect to t squared dt. In this case, our a and b will be 0 and 6 pi, since it's one full period. So we will define the integrand function. I usually like to define it separately to make it a bit simpler. So this is square root derivative of xt with respect to t squared, and then plus derivative of y of t with respect to t squared, and then we will integrate this between 0 and 6 pi. Notice I'm integrating with respect to t here. Now, this is quite a complicated integration, and as you can see, it's actually taking me quite a long time to calculate. So we'll wait until it's done. And here we have the answer. So it didn't actually calculate anything. As you can see, it's just very, very big expression. However, we can use n function here to estimate this so that we see what it equals to, at least approximately, in decimal notation. Now this calculation will take me a bit longer to calculate, and so I will just skip right away to the answer. And here's the answer. So it took me about 40 seconds to get this answer. So when you are doing your problem set, especially when you're calculating these long integrals, be patient and give your computer a bit of time to actually calculate it. Depends how strong your computer is. It can take up to a minute sometimes to do this calculation. Lab 6 will consist of 3 problems. In the first problem, you will be given a function and you will be asked to find a few Maclaurin series of different degrees and try to figure out how good are the approximations. In the second problem, you will be given a very complicated integral called elliptic integral of type 1. This integral is impossible to solve by hand, and so we will be estimating it using Taylor series. Finally, in the third problem, you will be given 2 different parametric functions, and you'll be asked to draw them and find the arc length. For one of them, you also will have to figure out the period